Right now, every major space agency on Earth is spending billions to reach a world where you cannot breathe, cannot grow food in the soil, cannot step outside without absorbing enough radiation to rewrite your DNA, and cannot survive a single dust storm without sealing yourself inside a pressurized coffin. Mars is the default plan. But 1,300 million kilometers further out, orbiting Saturn, sits a moon with a thicker atmosphere than Earth, lakes of liquid hydrocarbons, no deadly radiation at the surface, and enough chemical energy to power a colony for centuries. Its name is Titan. Almost nobody is talking about it seriously. The science says they should be. If you are ready to see why everything you were told about our future in space might be wrong, tap that like and subscribe button. I genuinely appreciate your support for the channel. Now, get yourself comfortable. Let's begin. The story of Mars begins with a dot of red light wandering across the night sky. Ancient Babylonian astronomers tracked it 3,000 years ago, scratching its movements onto clay tablets in careful cuneiform. The Egyptians called it Herdesha, the Red One. The Greeks named it Ares, after their god of war. The Romans gave it the name that stuck. Every civilization that learned to look upward noticed Mars because it was bright, it was close, and it moved in a way that demanded explanation. That instinct, to fixate on the nearest visible thing and assume it must be the most important, has driven every major decision humanity has ever made about its future beyond Earth. When Galileo Galilei pointed his crude refracting telescope at Mars in 1610, he saw something no human had seen before. Not a point of light like a distant star, a disk. A physical world with measurable dimensions hanging in the black. Over the following 2 centuries, telescopes improved. Astronomers sketched surface features that seemed to shift with the seasons. They measured the Martian day at roughly 24 hours and 37 minutes, eerily close to our own. They observed polar caps that grew during winter and retreated during summer, mimicking the rhythm of Earth's ice sheets. Among all the worlds visible from our planet, Mars appeared uniquely familiar. It looked, from a distance, like a colder, drier version of home. Then came the canals. In 1877, Italian astronomer Giovanni Schiaparelli used a relatively modest telescope to map linear features on the Martian surface. He called them canali, an Italian word meaning channels. English-speaking astronomers translated this as canals, a word that implied artificial construction rather than natural geology. The mistranslation ignited one of the most consequential scientific errors in history. Percival Lowell, a wealthy American businessman with a passion for astronomy, seized on the idea. He built an entire observatory in Flagstaff, Arizona, dedicated to studying Mars. Through years of painstaking observation, he mapped an intricate network of straight lines crossing the Martian disk. He published 3 books arguing that an advanced civilization had engineered a planet-wide irrigation system, transporting water from the polar caps to the dying equatorial deserts in a desperate bid for survival. The theory was elegant, emotionally compelling, and completely wrong. But it did something irreversible. It branded Mars in the human imagination as the planet most likely to harbour intelligent life. H.G. Wells published The War of the Worlds in 1898, and the Red Planet became permanently embedded in Western culture as Earth's twin, humanity's rival, and eventually humanity's backup plan. That cultural branding has never faded. It simply evolved. The Martians of Wells became the terraforming dreams of Kim Stanley Robinson, the corporate colonization visions of science fiction cinema, and eventually the PowerPoint presentations of billionaire rocket engineers. The through line from Lowell's canals to modern Mars settlement proposals is unbroken. Improved telescopes in the early 20th century revealed no linear features on the Martian surface. The canals were optical illusions, artifacts of the human brain's tendency to connect faint, random markings into patterns. But by the time the illusion was debunked, Mars had already won the cultural contest. No other planet had a comparable mythology. No other world occupied the same position in public consciousness. When the space race began in the late 1950s, both superpowers aimed for Mars almost immediately. Not because the science uniquely demanded it, but because the story already existed. Mars was where you went next. Everyone knew that. The only question was who would get there first. The Soviet Union launched Mars 1 in 1962, the first spacecraft aimed at another planet. It failed, losing communication during transit. Over the following decade, both the Soviets and Americans sent mission after mission. Most crashed, lost signal, or missed the planet entirely. Mars was close enough to attempt, but far enough to punish every shortcut. The early failure rate exceeded 70%, earning Mars a grim reputation among mission planners as the graveyard of spacecraft. The first successful flyby came in 1965. NASA's Mariner 4 passed within roughly 10,000 kilometres of the Martian surface and returned 22 photographs. Those grainy black and white images changed everything. They showed a barren, cratered landscape resembling Earth's moon far more than Earth itself. No canals, no vegetation, no signs of civilization or even basic habitability. The atmosphere was far thinner than optimists had hoped. Mars looked dead. A lesser destination would have been abandoned at this point. The romantic vision had been shattered. The surface appeared hostile and lifeless. But instead of retreating, the scientific community doubled down. The very bleakness of the landscape made Mars a puzzle worth solving. If the planet had once been warmer and wetter, as certain geological features hinted, where had the water gone? If life had once existed in that warmer epoch, could traces survive in the soil or ice? Each disappointing answer generated 10 new questions. Mars became not a destination for dreamers but a laboratory for scientists, and laboratories attract funding. NASA sent Mariner 9 in 1971. It became the first spacecraft to orbit another planet, and its photographs revealed a Mars far more dramatic than those first 22 images had suggested. Olympus Mons, a shield volcano roughly 22 kilometres tall, dwarfed anything on Earth. Valles Marineris, a canyon system stretching over 4,000 kilometres, could swallow the Grand Canyon without noticing. Most tantalizingly, the images showed channels and valley networks that appeared carved by flowing liquid, possibly water, possibly billions of years ago. Mars had a geological history. It had a story, and stories keep funding alive. Then came Viking. In 1976, NASA landed 2 spacecraft on the Martian surface. Viking 1 and Viking 2 transmitted the first colour panoramic images from another planet's ground. A rocky desert stretched to the horizon under a sky-tinted butterscotch by suspended dust. The landers scooped up soil and performed 3 biology experiments designed to detect microbial life. The results were agonizing. One experiment, the labeled release test, produced a positive signal that some scientists still argue could indicate biological activity. The other 2 experiments returned negative or ambiguous results. The majority consensus declared Mars sterile, but the debate never fully closed. That lingering ambiguity, that maybe, became another engine of sustained interest. Viking cost roughly $1 billion in 1976 currency, equivalent to over $5 billion today. The missions were engineering triumphs, but did not deliver the transformative discovery that sustains political enthusiasm. For nearly 2 decades afterward, Mars exploration entered a quiet period. No new landers arrived, budgets shrank, public attention drifted. The space shuttle program consumed NASA's resources and ambition. Mars waited. The revival came in the mid-1990s. NASA adopted a philosophy of faster, better, cheaper under Administrator Daniel Goldin. Mars Pathfinder landed on the 4th of July, 1997, delivering Sojourner, a rover roughly the size of a microwave oven, to the Martian surface. The mission cost a fraction of Viking and captured enormous global attention. Sojourner's images of a small robot navigating Martian rocks became iconic. amplified by the early internet in ways that no previous space mission had experienced. People around the world watched a wheeled machine explore another world in near real time. The emotional connection to Mars was re-established. From that point, Mars became the permanent centerpiece of planetary exploration. Spirit and Opportunity landed in 2004. Opportunity was designed for a 90-day mission and lasted nearly 15 years, traversing over 45 kilometers of Martian terrain. Curiosity arrived in 2012 aboard a revolutionary Skycrane landing system, carrying the most sophisticated analytical laboratory ever sent to another world. Perseverance touched down in 2021, accompanied by Ingenuity, the first powered aircraft to fly on another planet. Each mission carried more capable instruments than the last. Collectively, they confirmed that liquid water once flowed on the Martian surface in substantial quantities, that organic molecules exist in Martian rock, that the planet's geological diversity rivals Earth's in complexity, and that the conditions for ancient microbial life may once have existed. The international community followed NASA's lead. The European Space Agency sent Mars Express into orbit in 2003. India's Space Research Organisation successfully placed Mangalyaan around Mars in 2014 on its first attempt, for a total mission cost of approximately $74 million, less than the production budget of many Hollywood films. China landed the Zhurong rover in 2021, becoming the second nation to operate a rover on Mars. The United Arab Emirates sent the Hope orbiter into Martian orbit the same year. Mars became the most visited world in the solar system after Earth, not because the science uniquely required it above all alternatives, but because the infrastructure existed, the cultural expectation was cemented, and the orbital mechanics cooperated. Those orbital mechanics deserve close attention, because they form the practical backbone of Mars's dominance. Mars orbits the Sun at an average distance of approximately 228 million kilometers. At its closest approach to Earth, called opposition, that distance shrinks to roughly 55 million kilometers. Favorable launch windows open every 26 months, when the planets align for minimum energy home and transfer trajectories. A spacecraft using conventional chemical propulsion reaches Mars in approximately 6 to 9 months. Communication signals, traveling at the speed of light, take between roughly 3 and 22 minutes each way, depending on orbital position. These numbers are large by human standards but manageable by engineering standards. The delta-v budget reinforces the pragmatic case. Delta-v is the total velocity change a spacecraft must achieve across all maneuvers in a mission, from launch through orbital insertion and landing. The trans-Mars injection burn from low Earth orbit requires approximately 3.6 kilometers per second of delta-v, with additional velocity changes needed for Mars orbit insertion and landing. A round-trip crewed mission, including Mars orbit insertion, landing, ascent, and Earth return, demands roughly 16 kilometers per second total. This is achievable with existing chemical propulsion, though it requires large vehicles and careful staging. Compare this to the outer solar system. Jupiter lies roughly 5.2 astronomical units from the Sun, over 5 times farther than Earth. Saturn orbits at 9.5 astronomical units, nearly 10 times Earth's distance. Reaching Saturn's moon Titan with current propulsion technology requires either enormous amounts of fuel for a direct transfer or multiple planetary gravity assists that extend flight time to 7 years or more. The Cassini spacecraft, which remains the only mission to orbit Saturn, launched in 1997, performed gravity assists at Venus twice, Earth once, and Jupiter once, and did not arrive at Saturn until 2004. Nearly 7 years of interplanetary cruise. A crewed mission to Titan faces delta-v requirements substantially higher than Mars. The exact figures depend on mission architecture, but even optimistic estimates using nuclear thermal propulsion place one-way transit at 4 to 6 years. Communication delay between Earth and the Saturn system ranges from approximately 67 to 87 minutes each way. A simple question sent from mission control and its answer returned takes nearly 3 hours. This is not an inconvenience. It is a fundamental operational constraint that changes how missions are designed, how decisions are made, and how emergencies are handled. Launch window frequency compounds the advantage. Mars windows repeat every 26 months with relatively predictable geometry. Windows for efficient trajectories to Saturn are less frequent, more variable, and more sensitive to the precise alignment of multiple planets when gravity assists are employed. The logistics pipeline to Mars is regular and well understood. The logistics pipeline to Saturn is intermittent and complex. These practical realities created a self-reinforcing cycle that has operated for over 60 years. Because Mars was closer, the first missions went there. Because early missions went there, engineering heritage accumulated. Because heritage existed, subsequent missions became cheaper and more reliable. Because missions succeeded, scientific knowledge grew. Because knowledge grew, future missions could be planned with greater precision. Because precise plans existed, funding agencies felt comfortable approving them. And because funding flowed, institutional momentum built until Mars became not just the leading candidate for human expansion, but effectively the only candidate taken seriously in mainstream space policy. Elon Musk amplified this momentum beyond anything government agencies had achieved. When SpaceX announced its long-term objective of establishing a permanent, self-sustaining city on Mars, the idea migrated from the realm of speculative science fiction into corporate strategy backed by real hardware development. Musk's Starship vehicle, currently the largest and most powerful rocket ever constructed, was designed from its inception specifically for Mars transit. The entire architecture, the stainless steel hull, the refueling concept, the payload volume, the landing profile, everything about Starship optimizes for one destination. The most ambitious private space program in human history is built around a single world. NASA's Artemis program, while focused on returning humans to the lunar surface, explicitly frames the Moon as a stepping stone to Mars. The Gateway station planned for lunar orbit will test deep space habitat systems intended for eventual Mars transit. The surface technologies being developed for Artemis, including resource extraction, habitat construction, and advanced life support, are directly positioned as Mars preparation. Every congressional testimony, every budget justification, every strategic roadmap connects the Moon program to the Mars endgame. The architecture assumes Mars is the destination. The Moon is just the rehearsal. China's space agency has announced plans for crewed Mars missions targeting the late 2030s to early 2040s. The European Space Agency collaborates with NASA on a Mars sample return campaign designed to bring Martian rock and soil to Earth laboratories for the first time. Russia has periodically announced Mars ambitions, though funding constraints have limited follow-through. Japan and India continue developing Mars-capable technologies. Every major spacefaring nation on Earth treats Mars as the next logical step for human presence beyond the Moon. The consensus is nearly universal. But consensus is not evidence. The fact that everyone agrees on a destination does not mean the destination is correct. It means the decision was made long ago by people who had less information than we have now, for reasons that were practical rather than optimal, and nobody has seriously revisited it since. Mars sits in our cosmic front yard. It has a day-night cycle almost identical to Earth's. It has confirmed water ice at the poles and beneath the surface at mid-latitudes. It has carbon dioxide that could theoretically be processed into oxygen and rocket propellant. Its surface has been photographed at sub-meter resolution by orbiting spacecraft. We have driven robots across its terrain for a combined distance exceeding 70 kilometres. We know Mars better than any world besides Earth. On paper, in a brochure, in a pitch meeting, it looks like a reasonable candidate for human settlement. But brochures are designed to sell, not to inform. The version of Mars that dominates public perception emphasizes the similarities to Earth and systematically understates the hazards. The atmosphere that exists is 95% carbon dioxide at less than 1% of Earth's sea level pressure. The water ice is buried under meters of toxic soil. The familiar day length shares a world with temperature swings of 80 degrees Celsius between noon and midnight. The radiation environment at the surface has no terrestrial analogue outside a nuclear accident exclusion zone. Mars became the default destination for human expansion, not because a thorough comparative analysis identified it as the best long-term option. It became the default because it was the first plausible option, the nearest world that looked vaguely survivable, the place we could actually reach with rockets we knew how to build. Every subsequent decision, every funding allocation, every engineering program, every cultural narrative built on that initial choice, until the choice itself became invisible. Nobody questions it because nobody remembers a time when it was questioned. There is an enormous difference between the nearest option and the best option, between the world you can reach first and the world where you could actually thrive, between planting a flag and sustaining a civilization. That difference has been buried under 60 years of institutional momentum, cultural expectation, and the simple human bias toward what is closest and most familiar. The problems waiting on Mars do not care about momentum. They do not care about cultural narratives or corporate roadmaps or congressional budgets. They are physical, chemical, and biological constraints that exist whether we acknowledge them or not. Radiation that rewrites cellular DNA, atmospheric pressure that boils exposed blood, soil saturated with compounds that poison human thyroid function, gravity that may be too weak to sustain healthy bone growth across a human lifetime. Every engineering diagram, every habitat concept, every terraforming timeline begins with the assumption that these problems are solvable. Some probably are, given sufficient resources and ingenuity. But some may not be. Not within decades, not within centuries, possibly not at all, within the constraints that Mars imposes. And the distinction between solvable problems and structural impossibilities is precisely the distinction that determines whether Mars is a destination or a dead end. Understanding that distinction requires examining the Martian environment not as a brochure presents it, but as physics dictates it. An understanding that demand honestly, without the softening filter of institutional optimism or corporate branding, means confronting what Mars actually does to the human body, to engineering systems, and to every assumption about self-sufficiency the moment you step off the lander and realize that the nearest help is months away and the air outside your visor is trying to boil your blood. Stand on the surface of Mars without a spacesuit and you will be dead before you have time to understand what killed you. The sequence takes roughly 15 seconds. Not from the cold, although the average surface temperature hovers around -60 degrees Celsius. Not from the unbreathable carbon dioxide atmosphere, although a single lungful would trigger immediate suffocation. You die because the atmospheric pressure is so catastrophically low that the moisture lining your lungs, the saliva on your tongue, and the fluid in your eyes begins to boil. Not from heat, from vacuum. The partial pressure of water vapor inside your body exceeds the total atmospheric pressure outside it. Your own biology tears itself apart because Mars cannot hold down enough air to keep liquid stable. The surface pressure on Mars averages approximately 600 pascals. Earth's sea level pressure is 101,325 pascals. Mars offers less than 1% of what your body requires to function. To grasp what that means in physical terms, consider that the pressure on Mars is equivalent to what you would experience at an altitude of roughly 35 kilometres above Earth, deep in the stratosphere, far above where even the highest flying military jets operate. Felix Baumgartner's record-breaking parachute jump from 39 kilometres required a fully pressurised suit rated for near-vacuum conditions. On Mars, those conditions are not found at extreme altitude. They exist everywhere, all the time, at ground level. There is no sheltered valley, no deep canyon, no low-lying basin where pressure climbs to safe levels. Valles Marineris, the deepest canyon system on the planet, reaches roughly 7 kilometres below the surrounding plateau. At its floor, atmospheric pressure rises to perhaps 1,200 pascals. Still barely 1% of Earth's. Still lethal. The entire planet is a pressure desert. This is not one problem among many. This is the foundational environmental reality from which nearly every other problem on Mars cascades. Because the atmosphere is functionally a near vacuum, it cannot perform any of the services that Earth's atmosphere provides as a passive, effortless, permanent life support system. On Earth, the air absorbs the majority of incoming ultraviolet radiation before it reaches the surface. The air incinerates incoming micrometeorites through frictional heating during atmospheric entry. The air moderates temperature swings between day and night by trapping thermal energy. The air maintains the surface pressure that keeps liquid water stable across most of the planet's surface. And the air provides the medium through which sound travels, wind erodes, weather cycles, and biological respiration operates. Mars has none of these benefits. Its wisp of carbon dioxide offers no meaningful ultraviolet shielding. Micrometeorites reach the surface with minimal deceleration. Temperature differentials between day and night routinely exceed 70 to 80 degrees Celsius because the thin atmosphere cannot buffer the transition. And liquid water is thermodynamically unstable across virtually the entire surface because the pressure sits at or below the triple point of water, the threshold below which liquid cannot exist regardless of temperature. Water on Mars does not flow and evaporate the way it does on Earth. It sublimates, transitioning directly from ice to vapor without passing through a liquid phase. Any exposed water you manage to produce would flash into gas before you could collect it in a cup. Every habitat, every greenhouse, every workspace, every corridor connecting one pressurized module to another must function as a pressure vessel, an engineered container maintaining an internal atmosphere roughly 170 times denser than the environment outside its walls. Every wall is a dam holding back the vacuum. Every window is a structural weak point. Every airlock is a controlled failure in that dam, opened and closed with meticulous procedure, because a malfunction does not mean discomfort. It means explosive decompression. It means death measured in heartbeats. Pressure vessel engineering is well understood. Submarines, spacecraft, aircraft cabins, all operate as pressure differential systems. But no pressure vessel ever built was designed to function continuously, without major overhaul for decades or centuries. Submarines return to port for maintenance on regular cycles. Aircraft cabins are inspected after every flight and undergo major structural reviews after defined numbers of pressurization cycles. The fuselage of a commercial airliner is certified for a finite number of cycles, typically tens of thousands, before the accumulated metal fatigue from repeated pressurization and depressurization mandates retirement. Spacecraft are designed for missions measured in months or years, not generational timescales. And even so, the International Space Station requires continuous maintenance of its pressure seals, regular leak detection, and periodic patching of micrometeorite damage. A Mars settlement that depends on maintaining pressure integrity across an entire built environment, without access to Earth-based manufacturing for replacement parts, faces a reliability challenge unlike anything engineering has previously attempted. Metal fatigues, seals degrade, micrometeorite impacts create slow leaks. Thermal cycling between Martian day and night stresses joints and welds with each rotation. Dust infiltrates mechanisms with a persistence that borders on malice. Every pressurized structure on Mars is subject to a slow, relentless assault by an environment that exploits the smallest flaw. On Earth, a building that develops a crack in its wall lets in a draft. On Mars, a crack in a habitat wall lets in death. The failure mode is not gradual, it is binary, sealed or breached, alive or dead. The radiation problem extends directly from the atmospheric failure. Earth is shielded by two interlocking defense systems. The magnetosphere, generated by our planet's spinning liquid iron core, deflects the vast majority of charged particles from the solar wind and channels them toward the poles, where they produce the aurora. The thick atmosphere absorbs most of what the magnetosphere misses, including the high-energy ultraviolet and X-ray radiation that would otherwise sterilize the surface. Together, these systems reduce the radiation dose at sea level to approximately 2.4 millisieverts per year, a level so low that most people never think about it. Mars lost its global magnetic field approximately 4 billion years ago. The planet's iron core cooled and partially solidified, slowing and eventually halting the dynamo process that generates a planetary magnetosphere. Without that magnetic shield, the solar wind began stripping away the Martian atmosphere, molecule by molecule, over hundreds of millions of years. The process continues today. The MAVEN orbiter, which has studied Mars's upper atmosphere since 2014, confirmed that solar wind erosion removes roughly 100 grams of atmospheric gas per second. That sounds small until you multiply it across geological time. Over 3.5 billion years, those grams per second add up to an ocean of lost atmosphere. The thin remnant that clings to Mars today is not a stable feature. It is the slowly diminishing residue of what was once a far more substantial atmospheric envelope, and it continues to shrink. The radiation assessment detector aboard the Curiosity rover has provided the most detailed measurements of the Martian surface radiation environment. The instrument records a baseline galactic cosmic ray dose of approximately 0.64 millisieverts per day. Over a full Earth year, that accumulates to roughly 233 millisieverts. This figure represents the steady background from galactic cosmic rays alone, the constant drizzle of high-energy particles produced by supernova remnants, active galactic nuclei, and other violent astrophysical processes throughout the Milky Way. On top of this background, solar particle events deliver acute dose spikes that can dramatically exceed the daily average. During a moderate solar event observed by Curiosity in 2017, the surface dose rate approximately doubled for several hours. Major solar particle events, occurring several times per solar cycle, can deliver hundreds of millisieverts in a single day to an unshielded surface location. NASA's career dose limit for astronauts is 600 millisieverts of total accumulated exposure. A single severe solar storm on Mars could approach or exceed that lifetime limit in one event. And solar storms do not announce themselves with sufficient lead time for a surface crew to always reach adequate shelter. The warning window from orbital detection to particle arrival at the surface can be as short as 15 to 30 minutes for the fastest solar energetic particles. The nature of galactic cosmic rays makes them particularly difficult to shield against. These particles, primarily protons and heavy nuclei, carry energies measured in billions of electron volts. They penetrate deeply into solid material. A galactic cosmic ray proton can pass through several meters of aluminium, rock, or regolith before losing its energy. Worse, when these particles interact with shielding material, they produce secondary radiation. The incoming particle shatters atomic nuclei in the shield, creating cascades of neutrons, gamma rays, and nuclear fragments that can be more biologically damaging than the original particle. This phenomenon, called secondary particle production, means that thin shielding can actually increase the effective dose rather than reduce it. Only very thick shielding, on the order of several meters of dense material, begins to provide meaningful protection against the most energetic galactic cosmic rays. Building habitats beneath 3 or more meters of regolith is frequently proposed, but constructing and maintaining such buried structures across an entire settlement introduces its own engineering complexity and limits the flexibility of surface operations. For a short-duration Mars surface mission lasting 12 to 18 months, the radiation risk is elevated but manageable through a combination of shielding, scheduling outdoor activities during lower risk periods, and accepting a moderately increased lifetime cancer probability. Astronauts on such missions would receive career doses comparable to what International Space Station crew members accumulate over extended stays. The risk is real but falls within the range that informed individuals might voluntarily accept for the sake of exploration. For permanent settlement, the calculation changes fundamentally. A person living on Mars for 30 years would accumulate roughly 7,000 millisieverts of galactic cosmic ray exposure without shielding. Even with 2 meters of regolith overhead, which reduces but does not eliminate the galactic cosmic ray flux, lifetime doses would substantially exceed any occupational exposure standard ever established on Earth. The biological consequences of chronic low-dose radiation at these levels include significantly elevated cancer risk, accelerated cardiovascular disease, cataracts, and emerging evidence of central nervous system damage, including cognitive decline. Animal studies using simulated galactic cosmic ray environments at facilities like the NASA Space Radiation Laboratory at Brookhaven National Laboratory have demonstrated measurable impairments in learning, memory, and executive function in rodents exposed to dose levels comparable to a multi-year Mars surface residence. These findings remain subject to debate regarding their applicability to humans, but they represent the best available experimental evidence. No human dataset exists for chronic exposure at Mars-equivalent radiation levels because no human has ever experienced such conditions. The reproductive implications are perhaps the most concerning unknown. Developing embryos and fetuses are exquisitely sensitive to radiation damage. Cellular division rates during early development are so rapid that radiation-induced DNA errors propagate through far more cell lineages than they would in adult tissue. The consequences range from elevated mutation rates to developmental abnormalities to pregnancy failure. No data exists on human reproduction in a radiation environment comparable to the Martian surface. No ethical framework permits the experiments that would generate such data. Any Mars settlement that intends to sustain itself across generations is conducting an uncontrolled experiment on human reproductive biology in conditions that terrestrial radiation protection standards would classify as unacceptable. Below the radiation, the soil itself presents a chemical hazard with no clean engineering solution. Mars regolith is permeated with perchlorate salts, chlorine-containing compounds detected by the Phoenix lander in 2008 and subsequently confirmed at multiple sites by Curiosity. Perchlorate concentrations range from approximately 0.5 to 1% by weight across measured locations. Some models suggest even higher concentrations in certain regions. On Earth, perchlorates are classified as toxic contaminants. They interfere with thyroid function by competitively inhibiting iodine uptake, disrupting the production of thyroid hormones that regulate metabolism, growth, and neurological development. The United States Environmental Protection Agency sets a reference dose for perchlorate exposure at 0.7 micrograms per kilogram of body weight per day. Martian soil contains concentrations millions of times higher than what terrestrial health standards consider safe. Any agricultural use of Martian regolith would require extensive chemical treatment to remove perchlorates before planting. The most straightforward method involves washing the soil repeatedly with water to leach out the soluble perchlorate salts. But this demands large quantities of water, which is itself a scarce resource that must be mined from subsurface ice deposits, melted and purified before use. Each kilogram of soil might require several litres of wash water, and the resulting perchlorate-laden wastewater must then be treated or disposed of safely, adding yet another processing step to an already resource-intensive chain. Biological remediation using perchlorate-reducing bacteria is theoretically possible. Certain anaerobic microorganisms on Earth metabolize perchlorate as a terminal electron acceptor, breaking it down into chloride and oxygen. Establishing and maintaining cultures of these organisms in sealed Martian greenhouses under controlled conditions is feasible in principle, but introduces biological system dependencies, contamination risks, and maintenance requirements that compound the difficulty of an already formidable agricultural challenge. The alternative is to abandon Martian soil entirely and grow all food hydroponically or aeroponically, using nutrient solutions mixed from imported or locally synthesized chemicals in sterilized water. This is the approach most Mars settlement designs adopt, but it eliminates one of the supposed advantages of landing on a planet with a solid surface. If you cannot use the ground beneath your feet for agriculture, you are farming in a controlled environment facility that could just as easily exist in orbit or on any other solid body. The Martian soil, far from being a resource, becomes an environmental contaminant that must be kept out of every facility, filtered from every air supply, and cleaned from every surface that contacts it. The dust that coats every Martian surface compounds the perchlorate threat. Martian dust is extraordinarily fine, with particle sizes averaging roughly 3 micrometers, small enough to penetrate deep into respiratory passages and resist clearance by the body's normal mucociliary defense mechanisms. This dust is electrostatically charged by interactions with ultraviolet radiation and atmospheric triboelectric effects, causing it to adhere aggressively to surfaces, infiltrate seals, coat optical instruments, and accumulate on solar panels with a tenacity that defies simple cleaning. The Apollo astronauts discovered that lunar dust, which shares similar electrostatic properties, penetrated suit joints, abraded visors, and irritated respiratory passages despite limited surface exposure times. Martian dust presents a comparable mechanical hazard with the added toxicological burden of perchlorate contamination. Any human activity on the Martian surface, any EVA, any airlock operation, any vehicle movement, will introduce dust into the habitat interior despite best efforts at containment. Airlock designs for Mars habitats incorporate dust mitigation features, including electrostatic precipitators, air shower systems, and suit ports that theoretically keep contaminated suits outside the pressurized volume. None of these systems achieve perfect containment. Over months and years of daily surface operations, dust accumulates inside the habitat. It settles on surfaces, suspends in the air circulation system, and coats equipment. Inhaled Martian dust delivers perchlorates directly to lung tissue. Combined with the fine particle size and the presence of iron oxide compounds that may generate reactive oxygen species in biological tissue, chronic dust exposure on Mars presents a respiratory and systemic health risk that has been compared, with appropriate caution, to the silicosis hazard faced by miners and industrial workers on Earth. Except on Mars, the dust is everywhere, inescapable, constantly replenished by wind, and chemically more toxic than terrestrial industrial dusts. On Earth, silicosis is preventable through engineering controls and personal protective equipment used during defined work shifts. On Mars, the exposure is continuous, and the entire planetary surface is the contamination source. Global dust storms represent another category of environmental threat that has no terrestrial parallel. Roughly every 3 to 4 Mars years, regional dust storms merge and expand into planet-encircling events that can persist for weeks or months. These storms do not generate the dramatic wind speeds of terrestrial hurricanes. Martian atmosphere is too thin for wind to carry significant kinetic energy, even at high velocity. A 200 km/h gust on Mars exerts roughly the same dynamic pressure as a gentle breeze on Earth. The danger of Martian dust storms is not wind damage, it is opacity. The storms loft billions of tons of fine particulates into the atmosphere, creating a pall so thick that solar radiation reaching the surface drops by more than 90%. The sky darkens. The temperature differential between day and night narrows as the dust absorbs and redistributes solar energy. The entire planet becomes shrouded. The 2018 global dust storm provided a devastating practical demonstration. Opportunity. The rover that had survived nearly 15 years of Martian operations, 60 times beyond its original 90-day design life, relied on solar panels for electrical power. As the storm intensified, atmospheric opacity rose until the rover's panels could not generate enough electricity to maintain even minimal heating of its critical electronics. On June 10, 2018, Opportunity sent its last transmission. Despite months of attempts to re-establish contact after the storm cleared, the rover never responded. The cold had likely damaged components that the depleted batteries could not protect. A machine that had outlasted its design life by a factor of more than 60 was killed not by mechanical failure, not by terrain hazard, not by equipment malfunction, but by weather. A natural, recurring, predictable feature of the Martian environment simply switched off its power supply and waited for the cold to finish the job. For a settlement dependent on solar power, A global dust storm represents a slow-motion crisis that can last for months. Power generation drops to a fraction of baseline. Life support systems that depend on electrical power, air processing, water recycling, heating, and lighting must either draw from stored reserves or selectively shut down non-essential systems and reduce consumption to emergency levels. The storm's duration is unpredictable. Some global events resolve within weeks, others persist for 3 months or longer. Engineering a power reserve sufficient to sustain a settlement through the longest plausible storm scenario requires either massive battery banks storing months of energy at full consumption rates, nuclear backup systems operating independently of atmospheric conditions, or both. The mass penalty for months of battery storage is enormous. The cost and complexity of redundant nuclear systems is substantial. The failure to provide adequate reserves means that a dust storm, a natural and recurring feature of Martian weather patterns documented across centuries of telescopic observation, could kill a settlement not through dramatic destruction, but through slow suffocation as reserves drain and system after system shuts down to conserve the remaining watts. Nuclear fission reactors are the most credible solution to the power reliability problem, and NASA has made meaningful progress with the Kilopower project, which demonstrated a small fission reactor producing approximately 1 kilowatt of electrical power using a uranium-235 core and Stirling engine conversion, with designs intended to scale to 10 kilowatts. A functional Mars settlement would require multiple reactors in the tens to hundreds of kilowatt range, providing continuous baseline power independent of atmospheric conditions. This is technically feasible but adds significant mass to the initial mission manifest, requires careful site selection for thermal management and radiation safety, introduces maintenance demands for systems that must operate continuously for years without access to terrestrial repair facilities, and creates a single-source dependency that itself represents a vulnerability. If the nuclear system fails and dust storms preclude solar backup, the settlement faces the same energy crisis from a different direction. Water extraction presents another link in the chain of compounding difficulty. Mars has water. This is confirmed beyond doubt. Orbital radar soundings have detected massive subsurface ice deposits at mid-latitudes. The polar caps contain water ice beneath a seasonal layer of carbon dioxide frost. The Phoenix lander directly observed water ice centimeters below the surface at its high-latitude landing site. But the presence of water and the availability of water are different things. The ice is buried. Extracting it requires excavation equipment that can break through frozen regolith at temperatures far below zero, transport the material to processing facilities, melt it using thermal energy that must itself be generated from limited power reserves, and purify the resulting liquid to remove perchlorate contamination and other dissolved salts before it can be used for drinking, agriculture, or electrolysis. Each step in this chain consumes energy. Mining equipment requires power, transport requires power, melting requires heat, purification requires filtration, and potentially chemical treatment. Electrolysis to produce oxygen and hydrogen from the purified water requires substantial electrical input. The total energy budget for water production on Mars is not trivial, and it competes directly with every other energy demand in the settlement: heating, lighting, air processing, food production, communications, and equipment maintenance. Water on Mars is not a tap you turn on. It is an industrial mining and processing operation that must run continuously with high reliability in an environment that degrades equipment through cold, dust, and radiation. Growing food closes the loop of compounding challenge. Even assuming perchlorate-free hydroponic systems, artificial lighting powered by nuclear or solar electricity, and purified water from subsurface ice, agriculture on Mars faces fundamental constraints. The thin atmosphere transmits enough solar radiation for marginal greenhouse illumination during clear conditions, but global dust storms eliminate even this contribution for weeks at a time. Any greenhouse relying partly on natural light must be engineered to survive complete light deprivation during storm seasons, while maintaining plant health through artificial supplementation. Temperature control within greenhouses requires continuous active heating against the extreme external cold, adding to the energy budget. Carbon dioxide for plant growth is abundantly available from the atmosphere, one of Mars's few genuine agricultural advantages, but every other input, water, nutrients, light, heat, must be manufactured or extracted at significant cost. The agricultural system inherits every vulnerability of the systems it depends on. Power failure means light failure, heating failure, and water pump failure simultaneously. A dust storm that reduces power generation cascades directly into reduced food production capacity. A water processing breakdown interrupts irrigation. Each subsystem is coupled to every other, and Mars provides no environmental buffer to absorb the shock when one link in the chain fails. Gravity presents what may be the most intractable challenge of all. Mars exerts a surface gravitational acceleration of approximately 3.7 meters per second squared, roughly 38% of Earth's value. This is substantially more than the microgravity experienced aboard the International Space Station, and it is reasonable to hope that Martian gravity provides enough loading to prevent the worst effects of weightlessness. But hope is not data, and the data does not exist. Every piece of evidence we have about human physiology in reduced gravity comes from microgravity research aboard the ISS and its predecessors. Astronauts in microgravity lose 1 to 2% of bone mineral density per month, particularly in load-bearing bones like the pelvis and femur. They experience muscle atrophy, cardiovascular deconditioning, fluid redistribution toward the head causing elevated intracranial pressure and vision impairment, and immune system dysregulation. Rigorous daily exercise protocols mitigate, but do not eliminate these effects over mission durations of 6 to 12 months. Longer missions show continued degradation despite exercise. Whether 38% gravity is sufficient to arrest or substantially reduce these effects is entirely unknown. No human has ever experienced sustained partial gravity. No ground-based analog can truly replicate the condition. Bed rest studies with head-down tilt simulate some fluid redistribution effects but cannot reproduce the whole body loading reduction. Short-duration parabolic flights produce seconds of Martian gravity at a time, far too brief for physiological adaptation studies. The only way to determine whether Martian gravity sustains human health over years and decades is to put humans in Martian gravity for years and decades and observe what happens. The experiment cannot be run in advance. The first long-term Mars residents are the test subjects. If Martian gravity proves insufficient for healthy long-term habitation, no engineering fix is available. You cannot increase the gravity of a planet. Centrifugal artificial gravity habitats could theoretically supplement gravitational loading, but these are complex rotating structures that must be engineered, constructed, and maintained on a planetary surface, essentially building space stations on the ground and defeating much of the purpose of settling a planet in the first place. The entire premise of planetary colonization assumes the destination provides adequate gravity for human biology. This assumption remains unverified for Mars, and it may remain unverified until humans actually live there long enough to find out whether their bones are dissolving. The reproductive question looms behind every other health concern. A self-sustaining colony must produce new generations. Pregnancy, fetal development, infant growth, and childhood maturation are all gravity-dependent processes that have been calibrated by 4 billion years of evolution in Earth's gravitational field. Animal reproduction experiments in microgravity have produced disturbing results, including developmental abnormalities, altered gene expression, and reduced viability. Whether 38% gravity avoids these outcomes is unknown. Whether children conceived and born on Mars would develop normally, reach physical maturity without skeletal deformities, maintain adequate cardiovascular fitness, and remain reproductively viable themselves is a question that currently has no answer. This is not a problem that money solves. This is not a problem that better technology addresses. If the human body requires a minimum gravitational threshold above 38% of Earth normal for healthy development and reproduction, then Mars is biologically incompatible with permanent human settlement, regardless of how much infrastructure you build there. The planet's gravity is a fixed physical parameter. It will not change. Not in a century. Not in a millennium. It is a property of the world itself, as immutable as its orbital distance from the Sun. Now stack every one of these problems on top of every other. A Mars settlement must simultaneously maintain pressurized habitats against near vacuum, heat those habitats against temperatures that plunge below -100 degrees Celsius at night, shield inhabitants against chronic radiation exposure that accumulates with every passing hour, manufacture breathable air from an atmosphere that is 95% carbon dioxide, mine, and purify water from buried ice deposits using energy-intensive extraction processes, grow food in artificial environments that depend on every other system functioning correctly, manage toxic perchlorate-laden dust that infiltrates every surface operation, generate reliable power through dust storms that can last months, and do all of this with equipment that degrades continuously under the combined assault of cold, radiation, dust abrasion, and thermal cycling. Not one of these challenges exists in isolation. They are threaded together, each one a load-bearing wall in a structure where removing any single element brings the rest down with it. On Earth, if one system fails, the atmosphere provides a buffer. You can survive a power outage because the ambient air remains breathable and the ambient temperature is tolerable for hours or days. You can survive a structural failure because the building is not a pressure vessel and the outside air will not kill you. You can survive a water supply interruption because rain falls and rivers flow. Mars provides no equivalent buffer. The environment outside every habitat wall is lethal through multiple simultaneous mechanisms. Every failure threatens immediate or near-immediate lethality because the world itself offers nothing to fall back on. None of this makes Mars impossible for human presence. Robotic exploration has been brilliantly successful and will continue to yield scientific discoveries of profound importance. Short-duration crewed missions, lasting perhaps 18 months on the surface with pre-positioned supplies and reliable Earth communication, are within the reach of current or near-term engineering capability. These missions would be dangerous, expensive, and historically significant. They are achievable. But permanent, self-sustaining settlement, communities that grow and reproduce and survive independently of Earth resupply across generational timescales, faces a category of challenge that differs from exploration not merely in degree but in kind. Exploration requires surviving. Settlement requires thriving. And the Martian environment, as physics defines it rather than as brochures present it, imposes constraints on thriving that may prove structural rather than solvable. The radiation cannot be engineered away without impractical quantities of shielding mass. The gravity cannot be augmented by any known technology, short of building rotating habitats that negate the advantages of a planetary surface. The atmosphere cannot be thickened on any timescale relevant to human civilization. The soil is toxic. The water must be mined from buried ice and purified through energy-intensive processes. The air must be manufactured molecule by molecule. Every consumable must be produced locally at enormous cost or shipped from Earth at even greater cost. And every system required to accomplish these tasks must function continuously, without major resupply, in an environment that degrades equipment through cold, dust, radiation, and thermal cycling while offering no environmental safety net when things go wrong. Mars is not a backup Earth waiting to be activated. It is an alien world with a vanishingly thin toxic atmosphere, bathed in ionizing radiation, coated in poisonous dust, and possessing gravity that may be fundamentally incompatible with multi-generational human biology. It is the closest plausible destination. It is reachable with existing or near-term technology. These are genuine and significant advantages, but they are advantages of logistics, not advantages of environment. Farther out in the solar system, beyond the asteroid belt, beyond Jupiter, orbiting the ringed giant that ancient astronomers tracked across the sky, a world exists that addresses several of these problems through its own natural architecture rather than through human engineering. It has been dismissed for decades as too cold, too far, too alien. The science gathered over the past 20 years no longer supports that dismissal, and the conversation about where humanity should build its future deserves to include it. In November of 1980, Voyager 1 completed its flyby of the Saturn system and pointed its cameras at the largest moon orbiting the ringed planet. Scientists expected to see a surface. They saw nothing. A uniform orange haze blanketed the entire world, impenetrable to every optical wavelength Voyager's instruments could detect. The cameras that had returned breathtaking images of Jupiter's swirling storms, Io's erupting volcanoes, and the intricate structure of Saturn's rings could not see a single feature on Titan's surface. The moon was wrapped in a photochemical shroud so opaque that it might as well have been a featureless marble hanging in the dark. That failure to see was the first indication that Titan was profoundly different from every other moon in the solar system. The haze meant atmosphere, not the trace exospheres clinging to bodies like Ganymede or Europa, wisps so thin they barely qualify as atmospheric at all. Titan had a real atmosphere, dense enough to scatter light, thick enough to support weather, substantial enough to completely obscure the surface from space. Nothing else orbiting any planet in our solar system came close. Voyager's instruments could not photograph the ground, but they could measure what floated above it. The spectrometers and radio occultation experiments returned data that stunned the planetary science community. Titan's atmosphere was roughly 95% molecular nitrogen, the same gas that constitutes 78% of Earth's air. The remaining percentage consisted primarily of methane, with trace quantities of hydrogen, ethane, acetylene, hydrogen cyanide, and an exotic menagerie of organic molecules that had no business existing on a frozen moon, orbiting nearly 10 times farther from the Sun than Earth. But the measurement that truly shattered expectations was pressure. Titan's surface atmospheric pressure registered at approximately 147 kilopascals, 1.45 atmospheres, denser than the air pressing on your shoulders as you read this sentence. In a solar system filled with airless rocks, barren ice balls, and worlds where atmosphere means a few stray molecules per cubic centimetre, Titan possessed a nitrogen atmosphere thicker than Earth's. The only other rocky or icy body in the solar system with surface pressure even remotely comparable is Venus, whose crushing carbon dioxide atmosphere reaches 9,300 kilopascals, roughly 92 times Earth's pressure, and whose surface temperature of 460 degrees Celsius renders it irrelevant to any habitation discussion. Titan occupies a unique position. It is the only world besides Earth where a human being could stand on the surface and experience atmospheric pressure within a range the human body can tolerate without mechanical assistance. You would need thermal protection, you would need a breathing apparatus, but you would not need a pressure suit. Your body would not be fighting to hold itself together against vacuum. Your blood would not boil, your lungs would not rupture. The air outside, though unbreathable in composition, would press against you with a force your physiology recognizes as normal. Slightly more than normal, in fact. You would feel it against your skin, pressing gently inward, the way air is supposed to feel. In a solar system of vacuums and crushing extremes, Titan provides the one thing that no other extraterrestrial surface can offer, an atmosphere your body already understands. For 25 years after Voyager, that surface remained a mystery. Telescopes improved, adaptive optics on ground-based instruments, and near-infrared observations from the Hubble Space Telescope penetrated the haze sufficiently to detect crude brightness variations, hinting at continents and dark regions below. But genuine understanding required getting closer. It required Cassini-Huygens. The Cassini-Huygens mission remains one of the most ambitious robotic exploration campaigns ever conducted. A joint venture between NASA, the European Space Agency, and the Italian Space Agency. The spacecraft launched in October 1997 and arrived at Saturn in July 2004 after a 7-year interplanetary cruise that included gravity assists from Venus, Earth, and Jupiter. The Cassini orbiter entered Saturn orbit and spent the next 13 years conducting over 100 targeted flybys of Titan, using radar to map the surface throh the impenetrable haze. The Huygens probe, built by the European Space Agency, separated from Cassini in December 2004 and began its descent through Titan's atmosphere on January 14, 2005. What followed was one of the most extraordinary feats of robotic exploration in human history, and one of the least celebrated. A washing machine-sized probe, designed and built on Earth, entered the atmosphere of a moon orbiting Saturn at a distance of roughly 1.2 billion kilometres from the engineers who built it, and survived. The entry began at an altitude of roughly 1,270 kilometres, where the probe struck the upper atmosphere at approximately 6 kilometres per second. The heat shield absorbed the thermal pulse of entry, the shock layer of superheated gas ahead of it reaching over 12,000 degrees Celsius for a few violent seconds. Then the main parachute deployed, and Huygens began the longest atmospheric descent ever attempted on another world. 2 hours and 27 minutes of falling through an alien sky. No spacecraft had ever taken so long to reach a surface. No instrument package had ever sampled a continuous atmospheric column this deep on any body beyond Earth. During that descent, 6 instrument packages recorded atmospheric composition, temperature, pressure, wind velocity, electrical conductivity, and acoustic properties at every altitude from the upper haze layer to the ground. The data arrived at Cassini's receivers overhead, was stored on board, and later relayed to Earth across more than 1 billion kilometres of empty space. Each data point represented a measurement made in conditions no human had ever observed directly, translated into radio signals travelling at light speed for over an hour before reaching the nearest antenna on Earth. What Huygens found during that long fall permanently changed how scientists think about habitability in the outer solar system. The upper atmosphere teemed with complex organic chemistry. Ultraviolet radiation from the distant sun, combined with charged particle bombardment from Saturn's magnetosphere, drives continuous photochemical reactions in Titan's upper atmosphere, breaking apart nitrogen and methane molecules and reassembling them into increasingly complex organic compounds. Hydrogen cyanide, cyanoacetylene, acetonitrile, benzene, toluene, and a vast inventory of nitrile and hydrocarbon species form continuously and drift downward through the atmosphere as fine particulate matter. This photochemical smog is responsible for the orange haze that blocked Voyager's cameras. It is also, in chemical terms, extraordinary. No other world in the solar system produces organic chemistry at this scale and complexity through atmospheric processes alone. Consider what this means. On Earth, complex organic molecules are overwhelmingly associated with biology. Life produces organic chemistry. On Titan, organic chemistry is produced by sunlight and atmospheric physics operating on nitrogen and methane. The atmosphere is a chemical factory running continuously, powered by solar ultraviolet radiation and particle bombardment, producing tons of organic material every day and depositing it on the surface like a slow, ceaseless rain of carbon-rich snowflakes. The annual mass of organic material settling onto Titan's surface is estimated at several 100 million kilograms. Over geological timescales, this process has deposited organic layers meters thick across vast regions of the Moon. Titan is, in a sense, accumulating the chemical building blocks of more complex chemistry through a purely abiotic process that has been running for billions of years. Whether that chemistry has progressed toward anything resembling prebiotic complexity on the surface, or in subsurface niches where liquid water might interact with these organics, remains one of the most compelling open questions in planetary science. As Huygens descended below the main haze layer, the probe's cameras began to resolve surface features for the first time. The images revealed a landscape startlingly reminiscent of Earth, viewed from an aircraft window. Bright highland regions were cut by dark branching channels that converged into wider drainage networks flowing toward low-lying dark plains. The morphology was unmistakable. These were river valleys, not ancient eroded remnants like the channels on Mars that speak of water that vanished billions of years ago. These appeared geologically recent, possibly active. Liquid had carved these channels and might still flow through them periodically. The branching patterns followed the same mathematical scaling laws that govern terrestrial river networks, suggesting the same physical processes of erosion, transport, and deposition operating with different fluids at a different temperature, but obeying identical physics. Huygens touched down on a flat, damp surface and transmitted data for approximately 72 minutes before its batteries died. The images from the ground showed a scattering of rounded cobbles, roughly 10 to 15 centimeters across, composed of water ice. The rounding was significant. On Earth, rounded river cobbles acquire their smooth shapes through tumbling and flowing liquid over extended periods. These ice pebbles had been shaped by the same process, rolled and abraded in liquid methane currents that had carried them downstream and deposited them on a floodplain. The ground beneath the probe appeared dampened, as though recently moistened. The surface penetrometer registered a thin crust overlying a softer substrate, consistent with a surface that had been wetted and partially dried, like a riverbank after the water recedes. The gas chromatograph mass spectrometer detected a spike in methane concentration immediately after landing, suggesting the probe's residual heat had vaporized liquid methane from the saturated ground beneath it. Huygens had landed on a world with active surface hydrology. Not past tense, present tense. Titan had rain. It had rivers. It had a landscape shaped by flowing liquid. Not water. Methane. At the surface temperature of approximately minus 179 degrees Celsius, water ice is as rigid as granite. But methane, which exists as a gas on Earth, becomes a liquid on Titan. Ethane, a slightly heavier hydrocarbon, shares this phase behavior. Together, these two compounds constitute a working fluid that drives a hydrological cycle, operating on alien chemistry, but following physical principles identical to Earth's water cycle. Methane evaporates from surface reservoirs, rises into the atmosphere, condenses into clouds at altitudes where temperature and pressure cross the dew point, falls as rain, flows across the surface in rivers and streams, erodes terrain, deposits sediment, and collects in low-lying basins. The cycle is not metaphorical. It is not a loose analogy. It is the same thermodynamic process that drives weather on Earth, executed with a different molecule at a different temperature on a different world. Titan has weather. It has seasons. It has a climate driven by a familiar hydrological process operating with alien chemistry. Cassini's radar mapper, over 13 years of repeated flybys, assembled a comprehensive portrait of this world. The equatorial regions are dominated by vast dune fields, linear ridges of dark organic particulates stretching for hundreds of kilometers across flat plains. These dunes are composed of complex organic solids that precipitate from the upper atmosphere and accumulate on the surface like a slow, continuous snowfall of carbon-rich material. The dune fields rival the Sahara in scale and regularity, shaped by winds that circulate through the dense atmosphere with patient, persistent force. Unlike Martian dunes, which are sculpted by a thin atmosphere barely capable of lofting fine particulates during extreme storms, Titan's dunes are built by a dense atmosphere that moves material with the steady efficiency of a fluid 1.5 times denser than Earth's air. The mid-latitudes contain rugged terrain with mountain ranges, ridges, and canyons composed primarily of water ice bedrock. Cryovolcanic features have been identified in several regions, structures that may periodically erupt mixtures of liquid water and ammonia from the subsurface, analogous to silicate volcanism on Earth but operating with volatile ices instead of molten rock. The presence of cryovolcanism suggests an active interior geology, driven by tidal heating from Saturn's gravitational influence. The polar regions host Titan's most dramatic surface feature: hundreds of lakes and several vast seas of liquid methane and ethane cluster near the North Pole, with smaller concentrations near the south. Kraken Mare, the largest, spans roughly 400,000 square kilometres, comparable in area to the Caspian Sea. Ligeia Mare covers approximately 126,000 square kilometres. Punga Mare and dozens of smaller lakes fill depressions across the northern terrain. Cassini's radar altimeter measured the depth of Ligeia Mare at over 160 metres in places. These are not shallow puddles or transient accumulations that evaporate between observations. They are substantial, persistent bodies of liquid, deep enough to submerge multi-story buildings, stable across seasonal and potentially geological timescales, fed by methane rainfall and river systems that maintain their levels through a continuous cycle of evaporation, precipitation, and surface flow. Cassini observed clouds forming over the northern Lake District, tracked their movement across the sky, and watched them dissipate as methane rain fell toward the surface. The orbiter detected specular reflections from the lake surfaces, mirror-like glints of sunlight bouncing off perfectly smooth liquid, confirming beyond any remaining doubt that these were genuine bodies of liquid resting under an open sky. On one flyby, Cassini observed what appeared to be transient features in Ligeia Mare, bright patches that appeared, persisted for several orbits, and then vanished. Scientists interpreted these as possible nitrogen bubbles rising through the liquid or as suspended solids churned up by some process beneath the surface. The lakes of Titan are not static reservoirs. They are dynamic systems with their own internal processes, their own seasonal variations, and their own mysteries. Titan is the only world besides Earth where stable bodies of liquid exist on the surface in the present day. Mars has evidence of ancient water. Europa and Enceladus may harbour subsurface oceans beneath ice shells. But only Titan has open liquid sitting under an open sky, evaporating, raining, flowing, and collecting in basins you could sail across. The hydrological cycle is active right now, today, as you read this paragraph. The atmospheric composition and density produce a radiation environment that stands in stark contrast to the Martian surface. Titan's nitrogen column, at 1.5 times Earth's surface pressure, provides shielding against cosmic radiation that is functionally comparable to or exceeding Earth's atmospheric protection. Galactic cosmic rays, those deeply penetrating high-energy particles that present such an intractable problem on the Martian surface, interact with the dense atmospheric column above Titan's surface long before they reach the ground. The shielding is passive, permanent, and requires no engineering infrastructure to maintain. It is simply a property of the world itself. Saturn's magnetosphere contributes an additional protective layer. Titan's orbit carries it through Saturn's magnetic field for a significant portion of each roughly 16-day orbital period. During these intervals, charged particles from the solar wind are deflected by the planetary magnetosphere before reaching Titan. When Titan passes briefly beyond the magnetosphere's boundary into the direct solar wind, the thick atmosphere compensates. The combined effect produces a surface radiation environment estimated to be negligible, profoundly lower than the Martian surface, and potentially comparable to, or lower than typical background levels at sea level on Earth. This is not a marginal improvement. This is a categorical difference. On Mars, radiation is a structural threat that cannot be fully mitigated by any practical shielding architecture. On Titan, the atmosphere itself provides shielding as effective as Earth's. A human being standing on Titan's surface receives a radiation dose that their body can tolerate indefinitely. A human being standing on Mars's surface accumulates cellular damage with every passing hour. For any settlement expected to sustain human health across decades and support reproduction across generations, this distinction may be the single most important environmental variable separating the two worlds. The pressure differential between habitat interior and exterior reinforces the radiation advantage, with a structural engineering advantage of equal significance. A habitat on Titan does not need to function as a pressure vessel. The external atmospheric pressure exceeds 1 Earth atmosphere. A Titan habitat could, in principle, operate at slightly below ambient external pressure, meaning the structure experiences compression rather than tension. This is fundamentally safer. Consider the engineering implications. A pressurized habitat on Mars must contain roughly 1 atmosphere of internal pressure against an exterior near vacuum. Every square meter of wall surface bears approximately 10,000 kilograms of outward force. This loading is continuous, permanent, and unforgiving. Structural fatigue, seal degradation, micrometeorite puncture, or thermal stress cracking in any wall, window, joint, or airlock can initiate catastrophic depressurization. The habitat is a balloon. A Titan habitat, by contrast, operates in an environment where the pressure outside exceeds the pressure that would be maintained inside for human comfort. The structural load reverses. Instead of walls straining outward against vacuum, walls may experience modest inward compression from the denser external atmosphere. A structural flaw in a Titan habitat introduces cold air that seeps inward gradually. A serious maintenance problem, but not an immediately lethal one. The engineering margin between normal operation and catastrophic failure widens dramatically when the atmosphere outside is an ally rather than an enemy. The failure mode asymmetry between these two environments cannot be overstated for long-term settlement planning. Settlements must endure not just normal operations but cascading failures, equipment breakdowns, human errors, natural events, and unforeseen interactions between systems. The more forgiving the failure environment, the more resilient the settlement. Mars punishes every failure with the threat of instant death by vacuum exposure. Titan punishes failures with cold and atmospheric contamination. Serious threats that nonetheless allow time for response, repair, and recovery. Resilience, not peak performance, determines whether a settlement survives across centuries. Titan's surface and atmospheric chemistry provide a resource base that no other candidate world for human habitation can match outside Earth. The liquid methane and ethane in the lakes and saturating the near-surface regolith at high latitudes represent an effectively unlimited supply of hydrocarbon fuel. Combustion of methane with oxygen produces heat, water, and carbon dioxide, 3 products with direct utility for a settlement. Heat maintains habitable temperatures. Water supports biology and can be electrolyzed to produce more oxygen and hydrogen. Carbon dioxide can feed greenhouse plant growth. The oxygen required for combustion and respiration must be produced locally, but the raw material is literally underfoot. Titan's crust is predominantly water ice. Mining and melting this ice yields water. Electrolysis of water produces molecular oxygen and molecular hydrogen. The oxygen feeds combustion and life support. The hydrogen serves as a chemical feedstock, a fuel for fuel cells, or a component in ammonia synthesis when combined with atmospheric nitrogen. Nitrogen, the dominant atmospheric component, is directly available in gaseous form at ambient conditions. On Earth, nitrogen is essential for agriculture, serving as a key nutrient for plant growth typically supplied through ammonia-based fertilizers. The Haber-Bosch process, which synthesizes ammonia from atmospheric nitrogen and hydrogen, is one of the most important industrial processes in human civilization. On Titan, both feedstocks for this process, nitrogen gas and hydrogen from water electrolysis, are locally abundant. Agricultural fertilizer production does not depend on Earth resupply. The entire nitrogen cycle that sustains terrestrial agriculture has a chemical analogue available from local resources on Titan. The complex organic molecules continuously generated in the upper atmosphere and deposited on the surface provide additional chemical feedstock. Tholins, the brownish organic solids that compose the dune fields and surface sediments, contain carbon, nitrogen, and hydrogen in complex molecular arrangements. While their precise utility for manufacturing remains a subject of active research, they represent a locally available source of carbon and nitrogen compounds that could potentially serve as precursors for polymers, plastics, adhesives, and other materials essential for construction and maintenance. On Earth, the petrochemical industry derives thousands of distinct products from hydrocarbon feedstocks through refining and synthesis. Titan offers comparable raw materials in greater abundance, awaiting only the application of industrial chemistry that humans have practiced for over a century. The chemical self-sufficiency potential on Titan is qualitatively different from Mars. The contrast with Mars is difficult to overstate. Everything a Titan settlement needs for basic chemical self-sufficiency — energy, water, nitrogen, carbon — is available from local sources in quantities that dwarf what any other candidate world beyond Earth can offer. On Titan, the surface is covered with energy-dense fuel. The bedrock is a water reservoir. The atmosphere provides nitrogen for agriculture and industrial chemistry, and organic compounds rain continuously from the sky. The planet-scale chemical infrastructure exists naturally. Human engineering must tap into it rather than create it from scratch. Cassini's gravity science experiments revealed another dimension of Titan's potential. Precise tracking of Cassini's trajectory during close Titan flybys allowed scientists to measure the Moon's gravitational field with extraordinary accuracy. Variations in the field, combined with measurements of tidal flexing as Titan orbits Saturn, provided strong evidence for a global subsurface ocean of liquid water beneath an ice shell estimated at 50 to 100 kilometers thick. This internal ocean likely contains dissolved ammonia, which acts as an antifreeze, and may be in contact with a rocky silicate core at its base. The subsurface ocean is not directly accessible with current or near-term technology. Drilling through 50 to 100 kilometers of ice is beyond any engineering capability humans currently possess. But the ocean's existence has two important implications. First, it represents an enormous additional water reservoir that might eventually be accessible through deep drilling or exploitation of cryovolcanic conduits, where subsurface liquid reaches or approaches the surface. Second, the ocean-rock interface creates conditions relevant to prebiotic chemistry and potentially to biology, making Titan one of the highest priority targets in the search for extraterrestrial life, a scientific motivation that could sustain funding and political interest across the decades required for outer solar system exploration. NASA's Dragonfly mission will be the first dedicated return to Titan's surface since Huygens. Currently scheduled for launch in 2028, with arrival at Titan in the mid-2030s, Dragonfly is a rotorcraft lander, a nuclear-powered drone roughly the size of a large automobile, equipped with instruments to analyze surface composition, measure atmospheric properties, search for biosignatures, and characterize the habitability of Titan's surface environment. The mission design exploits a unique advantage of Titan's combination of dense atmosphere and low gravity in a way that no other planetary mission has ever attempted. In an atmosphere 1.5 times denser than Earth's, with gravity only 14% of terrestrial, the physics of powered flight become remarkably favorable. Lift is proportional to air density. Required thrust is proportional to gravity. On Titan, the air is denser and the gravity is weaker, meaning that for any given rotor size and rotation speed, a vehicle generates more lift while needing less of it. Dragonfly's 8 rotors, arranged in a coaxial configuration on 4 arms, work in conditions that are aerodynamically more favorable than any terrestrial helicopter encounters. The power required to maintain flight on Titan is a fraction of what an equivalent vehicle would demand on Earth. This is not a marginal advantage, it is a transformative one. Dragonfly is designed to fly from site to site, covering distances of roughly 8 kilometers per hop, then recharging its batteries on the surface using its multi-mission radioisotope thermoelectric generator before hopping again. Over its nominal 2.7-year primary mission, Dragonfly is expected to cover a total distance exceeding 170 kilometers, visiting multiple geologically distinct sites including dune fields, impact craters, and regions where water, ice, and organic materials may have mixed through cryovolcanic or impact processes. This mobility dwarfs anything achievable by wheeled rovers on Mars, where the total driving distance accumulated by Opportunity over nearly 15 years was roughly 45 kilometres. The flight capability is not just a convenience for a robotic explorer, it represents a fundamental advantage for any future human activity on Titan. Surface mobility on Mars depends on wheeled rovers that crawl across rocky terrain at speeds measured in meters per minute, limited by obstacles, slopes, sand traps, and battery capacity. On Titan, the same atmospheric density that shields against radiation and eliminates depressurization risk also enables efficient aerial transportation. Rotorcraft, airships, and fixed-wing aircraft could all operate in Titan's atmosphere with power requirements comparable to or lower than their terrestrial equivalents. Airships in particular become extraordinarily practical in Titan's dense, cold atmosphere, where buoyancy is easily achieved and wind speeds are moderate. A human settlement on Titan could conduct aerial surveys, transport cargo between distributed outposts, and explore distant regions at speeds and with a freedom of movement that surface-bound Mars operations cannot approach. Titan's atmosphere turns the entire Moon into navigable airspace. Titan was historically dismissed from serious habitation discussions for 3 reasons, and each deserves honest examination. Distance is real. Titan orbits Saturn at an average distance from the Sun of roughly 9.5 astronomical units, approximately 1.2 billion kilometers from Earth at closest approach. Transit times using conventional chemical propulsion and gravity assist trajectories range from 7 to 9 years, as demonstrated by Cassini's flight. Even with advanced nuclear propulsion systems currently under development, optimistic estimates place crude transit at 4 to 6 years. This is not a weekend commute. It is a journey that exceeds any human voyage ever attempted by orders of magnitude in both distance and duration. Cold is real. The surface temperature of -179 degrees Celsius places Titan among the coldest surfaces in the solar system. Every piece of equipment, every structural element, every mechanical system must function reliably at cryogenic temperatures that would shatter most terrestrial engineering materials. The thermal gradient between a habitable interior and the external environment approaches 200 degrees Celsius, demanding insulation systems of extraordinary capability and durability. Ignorance was perhaps the most powerful barrier. Until Cassini-Huygens, the scientific community simply did not know what Titan's surface looked like, what resources it offered, or how its environment behaved at ground level. Mission planning requires detailed environmental knowledge. Without it, engineers cannot design habitats, scientists cannot assess risks, and funding agencies cannot evaluate feasibility. Titan was a blank canvas, and blank canvases do not attract the billions of dollars required for human spaceflight programs. 2 of these 3 barriers are actively diminishing. Advanced nuclear propulsion concepts being developed for Mars missions, including nuclear thermal propulsion and nuclear electric propulsion systems, could reduce Titan transit times significantly. NASA's ongoing investment in space nuclear propulsion technology, driven by Mars mission requirements, produces systems equally applicable to outer solar system trajectories. The technology development path for reaching Titan faster runs directly through programs already funded for Mars. Every dollar spent developing nuclear propulsion for a faster Mars transit simultaneously develops the capability for a feasible Titan transit. The engineering is converging whether the institutional intent recognizes it or not. The ignorance barrier has largely collapsed. Cassini-Huygens provided a comprehensive environmental dataset for Titan's surface and atmosphere that exceeds in many respects what was available for Mars when human mission planning began in earnest during the 1960s. We know the atmospheric composition, pressure profile, and temperature gradient from surface to upper atmosphere. We have radar maps of terrain spanning most of the globe. We have direct surface measurements from Huygens. We have models of the methane cycle, the atmospheric chemistry, and the interior structure. Dragonfly will add ground truth data on surface composition, organic chemistry, and environmental conditions at multiple sites across varied terrain. By the time Dragonfly completes its mission in the late 2030s, The knowledge base for Titan's surface operations will be more robust than the knowledge base that supported the approval of the first crewed lunar landing program in 1961. Cold remains the genuine and undeniable engineering challenge. -179 degrees Celsius is not a problem that disappears with better data or faster rockets. It is a permanent feature of the environment that must be addressed through thermal engineering of every system, every habitat, and every piece of equipment that operates on the surface. But cold is a solved category of engineering problem. Cryogenic systems operate reliably on Earth in industrial, scientific, and aerospace applications. Liquid hydrogen storage at 20 kelvins, liquid helium systems at 4 kelvins, and superconducting systems approaching absolute zero all function within established engineering practice. Titan's surface temperature of approximately 94 kelvins is warmer than the operating conditions of many cryogenic systems already in routine use. The engineering heritage exists. Extending it to permanent surface habitats requires development, investment, and testing. But it does not require new physics. It does not require breakthroughs. It requires engineering, and engineering is what humans do. The conversation about humanity's future beyond Earth has been shaped by a single variable for 60 years. Proximity. Mars is closer, so Mars receives the missions, the funding, the political support, the cultural momentum, and the engineering heritage. This is rational behavior for an initial phase of exploration. You explore what you can reach, but exploration and settlement are fundamentally different activities with fundamentally different requirements. Exploration asks, where can we go? Settlement asks, where can we stay? If you change the question, the answer shifts, not entirely away from Mars. Mars remains valuable for scientific exploration and as a proving ground for deep space technologies, but toward a broader perspective that includes worlds previously dismissed as too far, too cold, and too strange. Titan does not solve every problem. Its gravity is lower than Mars. Its distance imposes transit times and communication delays that strain current mission architectures. Its cold demands thermal engineering of unparalleled scale. But it solves several problems that Mars cannot solve at all, problems that may ultimately determine whether a human settlement survives its first century or collapses under the accumulated weight of environmental hostility. But intuition is not evidence, and the only honest way to answer the question of where humanity should build its long-term future is to place these two worlds side by side, variable by variable, and measure them not by which one we can reach first, but by which one will still be keeping people alive 1,000 years after the first boots touch the ground. Place the two worlds on a table. Strip away the mythology, the institutional momentum, the cultural assumptions, and the corporate roadmaps. Ignore which one appeared first in a textbook, or which one a billionaire built a rocket to reach. Reduce each world to its physical parameters, the measurable environmental conditions that determine whether a human body can function, whether a habitat can endure, whether a community can sustain itself across generations without continuous life support from a home planet that sits months or years away. Then compare. Atmosphere is the variable that separates these candidates more decisively than any other. Mars provides approximately 600 pascals of surface pressure, less than 1% of what Earth offers, and far below the threshold required to keep liquid water stable or human tissue intact. Almost the entirety of that thin envelope is carbon dioxide, physiologically useless for respiration and chemically aggressive to exposed equipment over time. The atmosphere is too thin to shield against radiation, too thin to support aerodynamic flight with practical vehicles, too thin to buffer temperature swings between day and night, and too thin to prevent the immediate boiling of exposed biological fluids. In functional terms, the Martian atmosphere is an accounting entry. It exists on paper. It does almost nothing useful. Titan provides approximately 147,000 pascals, 1.45 times Earth's sea level pressure, composed overwhelmingly of molecular nitrogen. This atmosphere performs every service that Mars's atmosphere cannot. It blocks incoming cosmic radiation through sheer column density. It moderates surface temperature variation by trapping and distributing thermal energy. It supports powered aerodynamic flight with energy requirements comparable to or lower than terrestrial aviation. It eliminates the threat of explosive decompression from habitat structural failure, and it provides a nitrogen source that is industrially and agriculturally essential for any self-sustaining settlement. The pressure differential between these two candidates is not a matter of degree. It is a factor of 245. Mars has a trace. Titan has an ocean of air. Radiation separates the worlds with equal clarity. The Curiosity rover's instruments confirm a baseline galactic cosmic ray dose on the Martian surface of approximately 233 millisieverts per year, with acute spikes from solar particle events that can deliver hundreds of additional millisieverts in hours. Over a 30-year residence, cumulative exposure without shielding approaches 7,000 millisieverts, a dose incompatible with long-term health by any standard ever established in radiation medicine. Shielding reduces this burden but cannot eliminate it. Galactic cosmic rays at the highest energies penetrate meters of solid material and generate secondary particle cascades in shielding that can paradoxically increase biological dose for thin or intermediate shielding configurations. No practical Mars habitat architecture demonstrated to date reduces the galactic cosmic ray surface dose to Earth-equivalent levels. Titan's dense atmospheric column intercepts the same galactic cosmic ray flux before it reaches the surface. The shielding physics operates identically to Earth's atmosphere. High-energy particles interact with nitrogen molecules in the atmospheric column, losing energy through successive collisions and particle production events across a column mass comparable to Earth's. The surface dose is estimated to be negligible, potentially below terrestrial background levels at sea level. Saturn's magnetosphere supplements this protection during the portions of Titan's orbit that fall within the magnetic field boundary. The combined shielding is passive, permanent, maintenance-free, and effective against the full spectrum of space radiation, including the heavy iron galactic cosmic rays that are most difficult to stop with engineered shielding. For a settlement expected to endure decades and support human reproduction, this difference approaches the threshold of binary viability. Chronic radiation exposure at Mars-equivalent levels elevates cancer risk, accelerates cardiovascular disease, damages the central nervous system, and poses unknown but potentially severe threats to embryonic and fetal development. On Titan, the radiation environment permits indefinite human habitation without engineered shielding beyond what the atmosphere already provides. A child born on Titan's surface inherits the same radiation protection their ancestors evolved under on Earth. A child born on Mars inherits a lifetime of cumulative cellular damage that no known medical intervention can fully prevent. Gravity is the one variable where Mars holds a quantifiable advantage, and the advantage deserves honest acknowledgement. Mars provides 3.7 meters per second squared of surface gravity, roughly 38% of Earth's Titan, provides 1.35 meters per second squared, approximately 14%. Both are substantially below Earth normal. Neither has been tested for long-term human physiological compatibility. The entire body of evidence regarding human health in reduced gravity comes from microgravity research aboard orbital stations, an environment of effectively zero gravitational loading that differs qualitatively from both candidates. The critical question, what is the minimum gravity required for healthy bone remodeling, cardiovascular function, vestibular adaptation, and reproductive development, remains unanswered. It is plausible that 38% gravity is sufficient to prevent the worst effects of weightlessness, while 14% is not. It is equally plausible that both values fall below whatever threshold human biology requires, necessitating centrifugal supplementation on either world. Without experimental data from sustained partial gravity environments, the gravitational comparison between Mars and Titan remains a contest between two unknowns, one of which is numerically higher but neither of which is confirmed adequate. Mars likely has the advantage. The confidence interval around that advantage is enormous. Temperature is Titan's most visible disadvantage and the variable most frequently cited by those who dismiss it as a habitation candidate. The surface temperature of approximately -179 degrees Celsius is genuinely extreme. The thermal gradient between a habitable interior at roughly 20 degrees Celsius and the external environment approaches 200 degrees. Mars, with an average surface temperature of -60 degrees Celsius, presents a thermal gradient of approximately 80 to 100 degrees, roughly half of Titan's challenge. But temperature must be evaluated not as an isolated number, but as an engineering problem situated within the broader environmental context. On Earth, industrial cryogenic systems routinely manage temperature differentials exceeding 200 degrees. Liquefied natural gas processing plants, liquid hydrogen storage for aerospace applications, and superconducting systems all operate at temperatures comparable to Titan's surface. The insulation technologies required to maintain habitable interiors against this thermal gradient exist. Vacuum-insulated panels, aerogel composites, and multi-layer insulation systems developed for spacecraft thermal control provide demonstrated thermal resistance at the required scale. The engineering is demanding, but it is not speculative. It operates within known material science. The critical distinction is between the failure characteristics of thermal systems versus pressure systems. A thermal insulation breach on Titan is a gradual problem. Heat leaks outward. Interior temperature drops. Occupants notice, locate the breach, and repair it. The timeline for a thermal emergency is measured in hours or days, depending on the severity and the thermal mass of the habitat. A pressure containment breach on Mars is an immediate crisis. Air rushes outward into near vacuum. Pressure drops to lethal levels within minutes or less. The timeline for a depressurization emergency is measured in seconds. Survival depends on instantaneous automatic response or immediate proximity to a sealed refuge. Settlements must be designed not for optimal conditions but for worst-case failures. The question is not how well a habitat performs when everything works. The question is, how many occupants survive when something breaks? Thermal failure is recoverable. Pressure failure is frequently not. This asymmetry and failure consequence represents a structural safety advantage for Titan that compounds over the lifetime of a settlement. The more years a colony operates, the more failure events it will experience. A colony that can survive its failures persists. A colony where common failure modes are lethal does not. Surface chemistry diverges in ways that affect daily operations and long-term self-sufficiency. Mars regolith is contaminated with perchlorate salts at concentrations that render it toxic to human biology and corrosive to agricultural viability. The dust is electrostatically charged, fine-grained, pervasive, and composed in part of iron oxide compounds, with potential oxidative toxicity to lung tissue. Every surface interaction on Mars involves contact with this material. Every EVA tracks it into the habitat. Every mechanical system exposed to the environment accumulates it. Remediation is possible but energy-intensive and water-consuming, both resources that are themselves scarce and expensive to produce on Mars. Titan's surface materials present a fundamentally different chemical character. Water ice forms the structural bedrock, a resource rather than a contaminant. Organic sediments covering the surface consist of tholins and simple hydrocarbons precipitated from atmospheric chemistry. Liquid methane and ethane saturate the near-surface environment at higher latitudes and fill the polar lakes and seas. These materials are not toxic in the same acute biological sense as perchlorates. They are chemically useful. Hydrocarbons combust with oxygen to produce heat, water, and carbon dioxide. Water ice melts into the most essential consumable for any human settlement. Atmospheric nitrogen feeds agricultural and industrial chemistry. The surface chemistry of Titan is not a hazard to be mitigated. It is a resource inventory to be exploited. Energy production is the variable most frequently raised as a disqualifying disadvantage for Titan, and the concern has genuine substance. Titan receives approximately 15 watts per square meter of solar energy, roughly 1% of what reaches Earth and approximately 2.5% of what reaches Mars. Solar power generation on Titan is impractical for any significant energy demand. Panels large enough to power a settlement would need to cover areas measured in square kilometres, even under optimistic efficiency assumptions, and Titan's perpetual haze further attenuates the already feeble solar flux. But the energy discussion must extend beyond solar. Mars itself cannot rely exclusively on solar power. Global dust storms that periodically reduce Martian solar input by 90% or more for weeks at a time force any serious Mars settlement architecture toward nuclear fission as the primary reliable power source, supplemented by solar during clear conditions and battery storage for transient demand peaks. Nuclear power is not a Titangent-specific requirement. It is a baseline requirement for any permanent human outpost beyond Earth-Moon space. The difference is what comes alongside nuclear power. On Mars, nuclear fission is the only reliable energy source. If the reactor fails, there is no backup except stored battery capacity and whatever solar panels have been deployed and kept clear of dust. On Titan, nuclear fission provides baseline power, but the surface environment offers an independent secondary energy pathway. The combustion of locally sourced methane and ethane with locally produced oxygen generates thermal and potentially electrical energy using fuel that requires no mining, no processing, and no transportation beyond collection from the lakes and surface deposits where it already exists in liquid form. This is not a theoretical process. It is the same fundamental chemistry that powers natural gas heating systems across Earth, executed with fuel that Titan provides in quantities that exceed terrestrial petroleum reserves by orders of magnitude. A dual energy architecture, nuclear fission for electrical generation supplemented by hydrocarbon combustion for thermal energy and emergency backup, provides redundancy that a Mars settlement cannot replicate with local resources. Redundancy is not a luxury in settlement engineering. It is the difference between a colony that weathers equipment failures and a colony that dies from them. Now the honest accounting of what makes Titan extraordinarily difficult. Transit time is the dominant obstacle. Even under optimistic nuclear propulsion scenarios, a crewed mission to Titan requires 4 to 6 years of interplanetary flight each way. During transit, crew members endure prolonged microgravity exposure with its attendant physiological degradation, cosmic radiation accumulation outside the protection of any planetary atmosphere or magnetosphere, psychological stress from confinement and isolation, and the logistical burden of life support systems that must function continuously for years without resupply. The Mars transit of 6 to 9 months is itself a formidable challenge. Multiplying that duration by a factor of 5 to 8 transforms it into a qualitatively different category of mission. Artificial gravity during transit, potentially provided by rotating spacecraft sections or tethered vehicle configurations, could mitigate the physiological toll. Improved radiation shielding in transit vehicles addresses the cosmic ray exposure. Advanced closed-loop life support systems currently under development for Mars missions would need to demonstrate reliability across multi-year operational periods rather than months. None of these requirements are physically impossible. All of them demand engineering development beyond current demonstrated capability. Communication delay imposes operational autonomy requirements that exceed anything contemplated for Mars missions. The 67 to 87-minute one-way signal travel time between Earth and the Saturn system means that a Titan settlement cannot rely on Earth-based mission control for real-time decision-making during emergencies or routine operations. Every critical decision must be made locally. Every system must be diagnosable and repairable, with on-site expertise and resources. This demands a settlement population with broader technical skills, more comprehensive spare parts inventories, more capable local manufacturing, and more sophisticated decision support systems including artificial intelligence than an equivalent Mars outpost that can consult with Earth engineers within an hour. This autonomy requirement is demanding but not necessarily disadvantageous over the long term. A settlement that must operate independently from its first day develops self-sufficiency faster than one that can defer to Earth for guidance. The communication delay forces Titan colonists to become genuinely independent in ways that Mars colonists might delay for decades, leaning on their closer connection to Earth as a crutch that ultimately impedes the development of true self-sustaining capability. The cold is relentless and pervasive. -179 degrees Celsius is not an occasional extreme. It is the permanent ambient condition. Equipment must be designed for cryogenic operation from initial concept through end-of-service life. Lubricants must remain fluid at temperatures where most terrestrial oils solidify. Metals must be selected for fracture toughness at temperatures where many common alloys become brittle. Seals and gaskets must maintain flexibility and integrity across thermal gradients that would destroy most elastomeric materials. Every mechanical interface, every electrical connection, every structural joint must be engineered for an environment that attacks material properties continuously. These are serious engineering challenges. They are also well-characterized engineering challenges. Decades of cryogenic engineering for aerospace, industrial, and scientific applications have produced material databases, design standards, and operational protocols for precisely these conditions. Extending this heritage to permanent surface habitats requires investment and testing, but the fundamental material science is mature. Titan's low gravity at 14% of Earth normal may pose health risks more severe than Mars's 38%. While neither value has been experimentally validated for long-term human habitation, the lower figure increases the probability that supplementary gravitational loading through centrifugal systems will be necessary for bone health, cardiovascular maintenance, and safe pregnancy. Designing, constructing, and operating rotating habitat sections on a planetary surface adds substantial complexity to settlement architecture. The engineering is feasible. Large radius centrifuges producing partial gravity supplementation have been conceptually designed for space station applications, but it represents an additional infrastructure demand that Mars's higher gravity might partially or fully obviate. The surface illumination environment presents psychological and agricultural challenges. Titan's surface receives less than 1% of Earth's solar illumination, even at local noon, a dim amber glow roughly equivalent to deep twilight on Earth. The perpetual haze diffuses what light arrives into a dim, uniform glow without strong shadows or directional cues. The sky is orange-brown, never blue. Saturn is never clearly visible through the atmosphere. For humans evolved under bright, directional sunlight with blue skies and a clear day-night luminance cycle, Titan's permanent twilight would require careful environmental design. Interior lighting systems calibrated to circadian rhythms, bright common spaces with spectral characteristics mimicking terrestrial daylight, and perhaps virtual windows displaying Earth-normal sky conditions could mitigate the psychological impact. Agricultural lighting for food production must be entirely artificial, powered by the settlement's nuclear and chemical energy systems. This is standard practice for proposals involving subsurface habitats on Mars or the Moon, but on Titan it applies to every agricultural facility without exception. Return logistics deserve clear-eyed assessment. A crew launched to Mars can return to Earth after a surface stay of approximately 500 days, catching the next favourable launch window for a total round-trip mission duration of roughly 2 to 3 years. A crew launched to Titan faces a round trip measured in a decade or longer. This timescale makes short-duration exploratory visits impractical and transforms every crewed Titan mission into either a very long-duration expedition or a functionally permanent relocation. The psychological, logistical, and ethical implications of committing human beings to a journey from which return requires a decade of additional spaceflight are profound. Early Titan missions would likely need to be framed and accepted as settlement missions rather than expeditions. Supply chain fragility scales with distance and transit time. A critical component that fails on Mars can be replaced by a resupply mission arriving in 6 to 9 months from the next available launch window. The same failure on Titan requires years for replacement delivery. This demands that Titan settlements achieve a substantially higher degree of manufacturing self-sufficiency, parts redundancy, and repair capability than equivalent Mars outposts. The front-loaded investment in local production infrastructure is larger, the initial mission mass is greater, and the tolerance for equipment failure is lower until local manufacturing capability matures. These obstacles are real. They are formidable. They explain rationally why Mars dominates current planning. No responsible space agency ignores transit time, communication delay, and the cold when evaluating candidate destinations. But obstacles and impossibilities inhabit different categories. Every challenge listed above operates within known physics and has a conceptual engineering solution. Nuclear propulsion shortens transit. Artificial gravity mitigates flight duration effects. Autonomous systems address communication delay. Cryogenic engineering manages the cold. Hydrocarbon combustion and nuclear fission provide energy. Local chemistry supplies resources. None of these solutions are easy or cheap. None of them violate physical law. Mars, by contrast, presents at least two challenges that may not have engineering solutions at all. The radiation environment cannot be reduced to Earth-equivalent levels by any practical shielding architecture against the highest energy galactic cosmic rays. Gravity is fixed by planetary mass, and no technology alters that. If either of these fixed parameters falls below the threshold required for multi-generational human health, no amount of investment resolves the incompatibility. You cannot add atmosphere to Mars on any timescale shorter than centuries or millennia. You cannot add mass to increase its gravitational pull. These are properties of the planet itself, unchangeable by human action within any meaningful planning horizon. Titan's most severe challenges, distance and cold, are addressable through engineering that improves with time. Propulsion technology advances. Thermal engineering matures. Manufacturing capability develops. The obstacles shrink as human capability grows. Mars's most severe challenges, radiation and gravity, are physical constants of the planet. They do not improve with time. They do not respond to better engineering. They are the same today as they will be in 1,000 years. This asymmetry is the core insight that the comparison reveals. Mars offers challenges that are immediately manageable but may prove permanently limiting. Titan offers challenges that are initially daunting but may prove progressively solvable. The trajectory of difficulty over time favors Titan for any planning horizon, extending beyond the first generation of settlers. The strategic conclusion is not that Mars should be abandoned. Mars will be visited by humans, likely within the next 2 decades. It will host research outposts analogous to Antarctic stations, staffed by rotating crews conducting science of extraordinary value. It may host longer duration settlements that push the boundaries of human endurance in hostile environments. These achievements will be historic and worthwhile, but Mars should not monopolize the vision. The assumption that Mars is the only serious candidate for long-term human expansion beyond Earth is an artifact of proximity bias and institutional momentum, not a conclusion derived from comparative environmental analysis. When you compare the two worlds across the variables that determine whether a settlement thrives or merely survives, Titan presents structural advantages in atmosphere, radiation protection, failure tolerance, and chemical resource availability that Mars cannot match through any achievable engineering program. The comparison ultimately reveals not which world is better, because better depends on what you are trying to accomplish, but what humanity values in its expansion strategy. If we value speed of arrival, minimal transit risk, and near-term achievement, Mars is the correct priority. If we value environmental stability, long-term biological safety, and the structural foundations for a self-sustaining civilization that endures across centuries, Titan deserves a place in the conversation that it has never been granted. Neither world is easy. Both demand sacrifices, technologies, and commitments that current human civilization has not yet demonstrated the will to sustain. The honest answer is not Mars or Titan. The honest answer is that limiting the discussion to one destination impoverishes the strategy. The solar system offers multiple options for human expansion, each with different advantages and different costs. Treating Mars as the inevitable and exclusive answer forecloses possibilities that the science does not support foreclosing. Somewhere beyond the rings of Saturn, a moon with an atmosphere denser than our own orbits patiently through the outer darkness. It has lakes of liquid fuel on its surface, a sky that blocks the radiation that would slowly kill you on Mars, and enough raw chemistry to sustain an industrial civilization. It is cold beyond ordinary human experience and far beyond easy reach. But it has been solving problems for 4.5 billion years that we have not yet learned to solve for ourselves. The question is whether we are curious enough, patient enough, and honest enough to look past the nearest option and ask whether a harder journey might lead to a better home. That question does not have an easy answer, but it deserves to be asked, because the future of our species may depend less on how quickly we can leave Earth, and more on how wisely we choose where to go.